As we've learned, Gauss's law is one of the most important laws in the electricity and magnetism section of physics. In this video, we're going to learn about how to apply Gauss's law to objects with a continuous charge distribution. Basically, this means we're going to learn how to apply Gauss's law to two-dimensional and three-dimensional objects that are charged. Before we can see some examples of doing that, we're going to learn some guidelines about how to choose our Gaussian surface. Choosing the right Gaussian surface is the key to being able to apply Gauss's law to these problems. First of all, the basic general guideline is to choose a surface that's going to take advantage of the symmetry of the charge distribution so that the left-hand side of Gauss's law, the integral of E dot dA, becomes fairly simple. The surface you choose should satisfy one of four requirements. Or it is possible that it may satisfy more than one at a time. The four requirements are that the value of the electric field can be argued by symmetry to be constant over at least a portion of the surface. Another option is the dot product can be expressed as a simple algebraic product of E times dA, because E and dA are parallel. A third option, the dot product is 0 because E and dA are perpendicular. And the fourth, the electric field is 0 over a portion of the surface. The Gaussian surfaces that we choose, as you'll see in the next three example problems, will satisfy at least one of these conditions, but commonly they satisfy two or three of the conditions, making our left-hand side of our integral easier to evaluate. So let's try it out. In our first example, we're going to try to find the electric field at a point P, which is located at a distance r from a line of positive charge of infinite length and constant charge per unit length. So you'll see here I have my infinite line as well as my point P marked. I'm going to also mark off that this distance is little r as given to us by the problem. And we can also assume that this constant charge per unit length is lambda. So that's allowed to be in our final expression as well. The first step in doing any of these Gauss's law problems is figuring out what Gaussian surface would be most convenient to use here. We already know from previous knowledge that when we have a line of charge, the electric field emanates around it in all directions, kind of looking like this. In the plane of the paper, but it would also be sticking out of the paper, coming up at you, or going downward, or going into the paper. So we want to pick a Gaussian surface that will satisfy at least one of those four conditions. Typically, our Gaussian surfaces are really one of three options. Our options are typically a sphere, a cylinder, or a cube. Those are the three kind of most easily recognizable closed surfaces. Let's think about those three options. If we chose a sphere that passed through the point P, the electric field would not be constant over that surface. And there wouldn't be any spot where the electric field is 0 or the flux is 0. So that's really not our best option. So we're left with either a cube or a cylinder. Once again, choosing the cube, the four sides of the cube, rather not the left and the right face, but the top, bottom, and kind of front and back, those would have a flux, and the electric field would not be constant over those surfaces either. So that's not our best option. We're left with the last of those options, which is a cylinder. I'm going to draw a cylinder in here. It really doesn't matter how big of a cylinder you choose. You'll have to excuse my drawing abilities here. So there is a cylinder. This cylinder surrounds a portion of my line of charge, and the wall of the cylinder passes through the point P, which is where we're looking for the electric field. Thinking about those four conditions, this cylinder actually satisfies 3 out of the 4 conditions. So let's think back to what those conditions are. Condition 1 says the value of the electric field can be argued by symmetry to be constant over at least a portion of the surface. Well, if you think of the walls of the cylinder, those walls are all the same distance away from my line of charge, which means the electric field is constant over them. The electric field is not constant on my two faces, right here and right here, but we'll learn that doesn't matter. So this satisfies condition 1. Looking at condition 2, the dot product can be expressed as a simple algebraic product because E and dA are parallel. Again, thinking about the surface of my cylinder, not the two ends, the area vector would be pointed in the exact same direction as the electric field. Therefore, we can ignore the dot product and express it as an algebraic product. So condition 2 is satisfied. And condition 3 is satisfied because on these two faces, the dot product would be 0 because E and dA are perpendicular. That's what the A vector would look like for the right face, and that's what the A vector would look like for the left face, perpendicular to the electric field. So we have 3 out of our 4 conditions satisfied here, which is really convenient. That's going to make it even easier to apply Gauss's law. So now that we know what type of Gaussian surface we have, let's go ahead and take a look at Gauss's law. So we know Gauss's law says that the surface integral of E dot dA is equal to the Q that is enclosed by my Gaussian surface divided by epsilon naught. We'll work with both the left-hand side and the right-hand side of the equation kind of separately. So let's start off looking at the left-hand side of this equation. The manner in which we go about solving this is really important because showing our work on the AP test is where a lot of the points come up. So first of all, we know, as we already mentioned, that we can get rid of the dot product, but only for kind of the walls of the cylinder. And that's because that E and dA are parallel to each other. If you were doing this for the AP test, it might be good to make the note that that's why you're allowed to get rid of the dot product. And then we know that the electric field is constant for the walls of the cylinder, so I'm allowed to pull it out of the integral. And we also know that once we have an integral of just dA, that's the same thing as saying E times A. So that's our left-hand side of the equal sign. And every time you use Gauss's law, you basically should end up with E times A on the left-hand side. You just have to be able to argue as to why you're allowed to do that. So let's focus on the right-hand side of our equation. Before I plug anything in here, I want to point out that this is a linear charge distribution. And so it's equal to Q over L, right? Or I can also say that the Q that is enclosed by my Gaussian surface is equal to that charge distribution times the length of my cylinder. I'm going to use a different L there just to keep it separate from saying the length of the line, which is what the capital L represents. So coming back to the right-hand side of my equation, instead of Q enclosed, I'm going to put lambda times L in my equation. That divided by epsilon naught. And I'm going to leave that in here. So I end up having that electric field times the area, and that's the area of the surface area of just the walls of the cylinder, remember, because that's the only portion that has a flux. So E times A equals lambda L over epsilon naught. The next key is figuring out what to plug in for A. We're thinking about the area of the walls of a cylinder. It may help you to take a piece of paper and try rolling it into a cylinder. That's exactly the surface area that we're looking for. So if I were to do that, if I were to take a piece of paper and roll it into a cylinder, Really, I noticed that that piece of paper is actually a rectangle. And we know that area of a rectangle is length times width. Well, the length of my cylinder, or the length of my paper, I'm calling little l, and then the width of my paper ends up becoming the circumference of the circle. So 2 pi times little r. So that's what I plug in for A in my equation here. E times L times 2 pi r is equal to lambda L over epsilon naught. So we'll notice that there is a little L on both sides of my equation, so I can cancel that out. Solving for E gives me lambda divided by 2 pi epsilon naught r. Or another way of writing this, we know that K is 1 over 4 pi epsilon naught. So I could say that E is 2 times K times lambda divided by r. In my opinion, this is a fairly simple way of finding the electric field a distance r away from a line of charge. Because the problem told me that it was an infinite line of charge, it's totally fine to leave lambda in your final expression. Let's try another example. This time, we're going to apply Gauss's law to help us find the electric field at a point P, which is located a distance r from an insulating solid sphere of radius a that carries a total positive charge capital Q. And in this case, we're specifically told that r is greater than a. So let's mark some of those distances, some of those givens on our diagram here. So from the center of my sphere to P, that's r. Then it also tells me that the radius of my sphere is a. I'm going to mark those two on there. Again, our first task is to determine what Gaussian surface we should use. Basically, what is the geometry of the Gaussian surface? So thinking about this, as I mentioned in the previous example, we typically only use one of 3 Gaussian surfaces: a sphere, a cylinder, or a cube. And we want to find something where symmetry really helps us out a lot. This one should be pretty obvious as to what to use as your Gaussian surface. Since our object is a sphere, if I choose a sphere that has a radius of lowercase r, then I'm going to be able to argue, due to symmetry, some of those force instances there. One of those 4 cases. Really, actually, we'll find that this satisfies 2 of my 4 options in choosing a Gaussian surface. So my Gaussian surface is a sphere of radius r. Another thing to point out is it's really important to always draw your Gaussian surface. One thing that I didn't do here, just because it's a little bit difficult to do with this technology, but I commonly do when using a paper and pencil, is I usually draw my Gaussian surface with dashed lines rather than as a solid line. I find that that makes it easier so that you're not confusing your Gaussian surface with your object. You may find that to be helpful as well. Okay, let's take a look at Gauss's law, which tells me that the integral of E dot dA is equal to the charge that is enclosed by my Gaussian surface divided by epsilon naught. The first thing I always check is to see if I can get rid of the dot product. To get rid of the dot product, E has to be parallel to dA for all points. We know that when we have a solid sphere, the electric field points outward in every direction, and also my area vector would point outward in every direction. So I am allowed to get rid of that dot product. That's condition number 1. So condition 1 was met. Also, then I look to see if I can pull E out of the integral. Is the electric field constant everywhere on the surface? In this case it is, because our surface is always the same distance away from our sphere. So I pull E out of the integral, and then I'm left with E times the integral of dA, which is simply E times A. On the right-hand side of my equation, I think of how much charge is enclosed by my Gaussian surface. In this case, the charge enclosed is the total charge, which is given to us as capital Q. So all I need to do is plug capital Q into my equation here. Now, if I were to solve for the electric field here, I would have that E is equal to Q over epsilon naught times A. But unfortunately, capital A is not something that's given to us in the problem, so it shouldn't appear in our final answer. Instead, we should use some of the variables given to us. So then we have to figure out the surface area of a sphere, which, as we talked about in class, is equal to 4 pi r squared. Now we're talking about the surface area of the Gaussian sphere, which is why I'm using r squared instead of a squared here. Just as I did before, I can notice that I have 4 pi epsilon naught in the denominator here. So instead of writing E equals Q over 4 pi epsilon naught r squared, it would also be acceptable to say E equals KQ over r squared. Now that should seem familiar to you, because that's the electric field caused by a point particle. An interesting fact is that when you are outside of a solid sphere, it acts as if all of the charge is concentrated at the center of that sphere, which means the electric field is just like a point particle. We'll see in the next example what it's like when we're trying to find the electric field inside the sphere rather than outside the sphere. So for our final example, we have the same sphere here, but this time our point P is located inside the sphere. R is less than A. We still have the same amount of charge, and it should hopefully be pretty clear to you that we still want to use a Gaussian surface with the same geometry. In other words, just as before, our Gaussian surface is going to be a circle. Sorry for my kind of wiggly circle here. Also, just as before, the radius of our charged sphere is A, and the radius of our Gaussian sphere is little r. So, once again, we'll start out with the integral, surface integral of E dot dA is equal to Q enclosed divided by epsilon naught. And again, just focusing on the left-hand side of my integral here, E and dA are parallel for all points on my sphere, so I can get rid of the dot product. Because all points of my Gaussian surface are the same distance from the center, I can argue by symmetry that the electric field will be constant everywhere around that Gaussian surface, so I can pull that out. So I'm left with E times A. Now, just as before, figuring out the left-hand side of this equation was pretty easy. What we'll find is that the right-hand side is a little more complicated when we get inside our object. So, for starters, one thing I want to point out before we go any further is that the problem tells me that this is an insulating solid sphere. That's really important because, as we will learn, if the charge is not distributed evenly, in other words, if you have a conductor, the electric field inside of a conductor is 0. But because this is insulating, that means that charge is distributed uniformly. So, because this is a solid object, three-dimensional object, I use a volume charge distribution. So rho is Q over V. This would be the charge of the entire thing divided by the volume of the entire object. And I know that I'm also trying to plug something in for Q enclosed. Because it's a uniform charge distribution, Q enclosed would be the volume, charge density, times the volume of our Gaussian surface. Basically, I've just set up a proportion since rho is constant for my entire object. Now, as I'm thinking about the volume of the Gaussian surface, volume of a sphere is 4/3 pi r squared, and my Gaussian surface does have little r as its radius. And I apologize, I said r squared, but really I meant r cubed. So, one last step. We typically don't want to leave our charge density in there. So instead of rho, I'm going to have capital Q over V times 4/3 pi r cubed. And I'll finish this off kind of coming up over here. So I have Q times 4/3 pi r cubed. And that's over the volume of the entire insulating solid sphere, which is going to be 4/3 pi a cubed. As you see here, many things conveniently cancel out, such as those 4/3 and the pi. And so what I'm left with on my right-hand side is capital Q r cubed divided by a cubed. So I'll write that here for both sides. And then, of course, we want to solve for our field, since that's what we're looking for in the end here. So E is equal to Q r cubed over a cubed times capital A. Capital A is the surface area of the sphere, which we know is 4 pi r cubed. Now, I want to pause for a second. This A is the surface area of the Gaussian sphere, so it is little r squared here. And then we see that this r squared cancels out the cubed up there. And finally, we get our expression for the electric field inside an insulating solid sphere to be QR. Oh, I missed the epsilon naught somewhere. I forgot my epsilon naught on the denominator here. That's important. Just going to add that in. So capital Q times lowercase r divided by 4 pi epsilon naught a cubed. And just as we've done in the past examples, we can substitute k in so that E is equal to k q r over a cubed. An important thing to note is that as we get closer and closer to the surface, in other words, as r gets closer and closer to A, this equation for the electric field looks more and more like the equation outside of the sphere. Another way of saying that is that the electric field is a continuous function. So that if we were to look at the limit coming from one side versus coming from the other side, they end up giving us the same thing. Calculus likes it when we have continuous functions. In class, we'll practice even more Gauss's law and applying it, but hopefully this video serves as a way to give you a good introduction into how to use this really important law.